Hi. So now I want to get more deeply into the concept of electric current. The idea, well, first of all, the phrase electric current refers to a collection of charges that are in motion. Almost always, the moving charges are traveling along a fixed path. The one major exception that I can think of off the top of my head would be a lightning bolt. But in any case, if electric charge particles are moving from one place to another place, then we say that we have an electric current, a flow of charge. Very similar, of course, to the use of the same word current for water. A flow of water is a current in a river or in an ocean or something. So current means to move from side to side or from place to place. So electric currents. The charged objects that are flowing can be many different things. In a wire, which is perhaps the most common current, certainly the first one you probably think of, the objects that are moving are, in physical reality, almost always electrons. As it will turn out, and as I'll explain in a little while, in fact, we pretend that they are positively charged objects that actually flow, even though we know that it's actually, in fact, negative electrons that do the flowing in a wire. I've hinted at that before in previous lectures, and now the time is very close where I'm going to actually make all that very definite, very explicit, and perhaps even explain it. Okay. So in a typical battery, whether it's a flashlight battery or the little coin batteries that you have in devices, or your laptop battery, or the battery in your car, the charge carriers are typically ions of some type, chemical ions. Most of the time, in your car battery, for example, I believe it's an ion of an acid, H2SO4, of the added hydrogen or something. And so, but whatever the charged object is, it is moving from place to place, and when that's true, we have an electric current. Okay. I want to focus on the most common type of charge carrier, as I just said, are the electrons in a wire. So let's take a look at that. You might remember from chemistry that if you have doesn't matter what it is, plus 8. I don't know what 8 is. Maybe it might be carbon or something. Actually, let's do. I think copper. I want to say copper is 29. You'd think I'd look this up before I started my recording, but whatever. The point is, and my specific number might be wrong here, but whatever. 29 electrons. You remember from chemistry that they're arranged in imaginary spherical shells, orbitals, and the innermost orbital has 2 electrons, and then the next one out has 8, and then the next one out has 18, I believe it is, and so on, and whatever, and so it keeps on going. And in a metal, which, as I'm sure you know, is the most common type of conductor, certainly it's the only thing we make wires out of. In a metal such as copper, the electrons are arranged in such a way that what we find is that at the farthest possible distance from the nucleus, we get one single lone electron. Now, that electron, turns out, is very easily stripped off of the atom for 2 reasons. One, it's very far away from the nucleus, and so the Coulomb's law force binding it, the electrical force binding it, is much weaker for it than for any of the other electrons, which of course are closer to the nucleus. So there's that, first of all. And the other reason that this electron can be stripped off the atom very easily is because not only is it very far away from the nucleus, but in fact, although there may be 29 protons of positive charge in the nucleus, 28 of them are shielded by the intervening other 28 electrons. And so this outermost electron, rather than seeing a nucleus of a charge of plus 29, effectively only sees a nucleus of charge plus 1. And so the Coulomb force is reduced more for that reason as well. The result is this electron is very, very loosely, very weakly bound to the nucleus, and therefore can be stripped off very easily. And one way to do that is to put a one way to do that is to build a wire out of these atoms, a copper wire. And everything I just said about this one copper atom is true for all of the copper atoms in your wire. And so a way to disturb and to knock this electron off is to attach either end of this copper wire to one side and the other side of a battery, thus setting up a potential difference across the wire, thus setting up an electric field which creates an electric force on these charges and again knocking them loose. So that's what happens there. And these guys have a name, and again, you've probably heard about it in chemistry. Anyway, they are called conduction electrons, also known as a valence electron to chemists. Okay. So the electron, what it does once it's knocked loose, it tends to drift over to the next copper atom that's next door. And so it gets knocked loose. Do this in a different color. And it wanders over and attaches itself to this atom here, if that atom has had its conduction electron also knocked loose. And if so, then its electron went over to this atom, which then goes over to this atom, which goes over to this atom, and this is a current. Okay? You can see a really nice picture in your textbook. We'll talk about it in class, but this is the essential idea. One atom after the other after the other. I'll draw one more in just because. So this is how a current flows, and as I say, these are called conduction electrons, and we conduct a current. Now the speed at which these electrons move from atom to atom, you may be under the impression that the speed of the charges as they move through the wire is very, very high, possibly close to the speed of light. And your impression, if you have it, is caused most likely by the fact that when you flip on the light switch, the lights come on instantly. There's no perceptible delay. And so it's tempting to think, oh, well, that's because these charges get from the light switch to the lights, essentially instantaneously, speed of light. Not true at all. The fact is that the drift speed, drift speed or drift velocity is just a few centimeters per second, if even that. It's different for different types of conductors. Metals, it's a little bit faster, and in ionic fluids like battery acid and things like that, it's slower than that. Now, the reason that the lights come on essentially instantaneously is because the electrons that cause the light bulb to light were already present in the light bulb when you flip the switch. The only thing flipping the switch does is it establishes the potential difference that then energizes the conduction electrons. And so all of the conduction electrons in the entire wire start moving simultaneously. What does travel at near the speed of light is the electric force that the potential difference creates when you complete the circuit by turning on the light switch. So that causes all of the charges to start moving together, rather like all of the cars on a subway train or a railroad train. When one part of the train moves, the entire train moves all simultaneously because they're all connected. Okay. Then too, as far as the whole negative charges versus positive charge mystery, I want to remind you that a negative charge, let me remind you first of all, that these negative charges are moving, as charges always will, only in response to an externally applied electric field. This externally applied electric field is created, as I said, by the potential difference, the battery or Puget Sound energy or whatever that is connected to either side of your wire. And so if the electron, but remembering that the electrons are negatively charged, since the electrons in my drawing are moving that away, the external electric field causing this motion must be pointing in the opposite direction. So the drift velocity is this way, but the electric field is that way. Okay, we've known this all along, that the acceleration that an electric field creates on a negative particle, that acceleration always points in the opposite direction that the electric field vector points. Okay, so this is just an example of that. One other thing I want to tell you about, as far as understanding what a current flow is and how it works, now I'm going to draw you a picture of a wire at not the microscopic level, or at least less so. So this is supposed to be a piece of copper wire. Okay. And what I'm going to do is what I was saying a moment ago, which is I will create a potential difference across it. And what all that means really is I'm going to connect each end to the opposite sides of a battery. So this creates a potential difference here, and there's a certain subtlety that I'm going to talk about here in a moment. Anyway, so our negatively charged electrons, let's take a look. Remember that the rule is that charges always move spontaneously from a region of higher electric potential to a region of lower electric potential. So according to the way I've drawn this, it's high potential on this end, low potential on that end. All right, and so actually, I'm sorry. I want to reverse the direction of the battery for reasons that I'll explain in a moment. Okay. So start that over. Just point at different locations. Okay. So it's high potential over here, low potential over here, and so that means. No, I like it the other way. Okay. Well, let me not do it. Let me not screw this up. Let me make sure I like which way I'm going here. Yeah, no, I'm sorry. It's right this way. Okay. One more time. The rule is, as I was just saying, that charges will spontaneously fall from high potential to low potential. Having drawn it the way I've drawn it now, high potential over here, low potential over here, the charges aren't going to go directly through the battery. They instead are going to fall from the high potential end to the low potential end through this wire. Now, before you get totally confused, this brown stuff here is also a copper wire. All I've done is magnify it here for this horizontal bit so that I can point out some things that are happening. Okay, so, but that rule that I just quoted you, spontaneously moving from high potential to low potential, is, although it is always true, it is a little more complicated if the charge carriers are negative. Okay, so a positive charge would spontaneously go from here to there in that direction. Okay, but we're dealing with negative charge carriers, and so as we've talked about before when we were talking about potential, the negative charge carriers, in fact, will do the opposite of whatever a positive charge carrier would do. And so our electrons, in fact, are going to move this direction, and so counterclockwise. And in fact, that's why I was so careful about flipping the battery so that my direction of my current flow would match this drawing over here. There wasn't any particular crucial need for me to do that, but I thought, why not? Okay, so the electrons are moving such that they establish a current that we will say is flowing counterclockwise. And so what we have are a bunch of charges, negative charges, that are, and these are all conduction electrons now. I'm not suggesting that every electron on the atoms move. That's not true at all. Only the conduction electrons actually move. Okay, so what's happening then is that negative charges are, and see, I drew it wrong. Other direction, sorry. Negative charges are moving from the negative end of the battery to the positive end, again, opposite the direction that a positive charge would flow. And so, and then your drift velocity in the long straight wire bit is that direction. And so, again, every one of these electrons that I've drawn there are conduction electrons. And then in the non-magnified portion of my wire, I just colored it red, showing that the current is flowing in that way. Okay, so that's a different, again, a qualitative introduction to the idea of current flow. However, there's a few more ideas I need to communicate before I can start calculating some important properties of this wire, and we're heading for an answer to the question of, back a few lectures ago when I lit the light bulb with the capacitor, why did the light bulb light in the first place? And so I think I'll stop this recording here, and in the next recording we'll develop a few more ideas and start doing some calculations.